Okay, you guys are in for it because we've got part 3 of Ensembles today. This lecture is about stacking, which is another ensemble algorithm similar to boosting and bagging, sort of, and then intelligence architectures, which is how do you take this notion of ensembles and combining a bunch of models together and do it in a way that's not only accurate, but is also supportive of the team and supportive of long-term success. That's what we're talking about today. Now, clicking in, remember the first 2 lectures, we had 2 slides that came first. One was like about what are ensembles and why, and the second one was a couple of methods for thinking about ensembles. So I'm not going to do those slides 3 times in 3 consecutive lectures, but keep it in mind. And we'll jump right into the stacking algorithm here. And here we go. We're going to click through it. 3, 2, 1, we go. So you have a training set for your stacking algorithm, and now your base models are of different types. And that's one of the big differences between stacking and boosting and bagging. You would take your training set and you'd learn a decision tree on it, and you'd learn a linear model on it, and you'd learn a neural network, and maybe you'd learn different variants of some of these same model types with different hyperparameter settings. Anything you want to do, you learn a whole bunch of base models. That's difference number 1. And here comes difference number 2. You take those base models and you use their output to produce another training set. And this is called the meta training set. And this training set you'll use to train the meta learner, which is going to learn how to combine those base models and make a final prediction. Okay, that's the algorithm. Let's go through it in a little bit more detail, maybe 2 or 3 more times to make that stick a little bit better. And for some reason, I always like to say where parallel training is possible. I don't know why I like to do that. I like to do it. But you can see that on the original training set, you have to learn K base models, and each one of these things is done totally in parallel, at least for that base model training step. And potentially different model types, different hyperparameter settings. You want to do what here? Well, what you're trying to do here is learn the same concept many different ways with variants, different approaches to the problem, so that problems can cancel themselves out downstream. You don't want to learn the problem the same way K times. That's not going to help at all. So you've learned the problem a bunch of different ways. Now you create this meta training set. And the way you do it is that the labels for the meta training set are the same as the labels for the initial training set over here. So you keep the labels exactly the same, but what you change is the features. And the meta training set has 1 feature per base model. So if you have 7 of these base models, the meta training set will have 7 features. And the first feature for the meta model is the prediction of the first base model. And the second feature for the meta model is the prediction for the second base model. So you could see if everybody predicts yes, you go. If everybody predicts, I'm not sure, but maybe, and enough people predict that, you go. So it's a little bit different than voting. It is letting each of these experts, base models, sometimes they're called experts, so this is a collection of experts. Each expert is able to say, hey, here's my best guess. And then you have some meta expert that's able to look down and say, well, you know what, these 3 guys are usually the most accurate experts, so I will trust them if they agree, but if they don't agree, then these guys tend to help most when expert number this one is wrong, and then these other guys over here help most when expert number there is wrong. You can get these complex interrelationships between the base model and the final prediction that you're going to try to make. And at runtime to do this, you would create the training sample in memory in your application, pull together all the logs, create the training vector. You'd pass the training vector to each of your base models, take their predictions, and produce this meta training sample or meta evaluation sample at this point, and then apply the meta model to that sample and get your final prediction. And so that's how it works. Let me just fade out of the way here so I'm able to pull up this pseudocode, this little, we're even going to get to pseudocode on the next slide. I'm just going to go through this a few times. So here we go again. Apply the base learners, decision tree, logistic regression, neural network. You could use bagging, you could use boosting, you could even use naive Bayes. Why not? In this context, probably wouldn't hurt. The meta learner, the features are the base learner's predictions, and the labels are the labels from the original training set. And then the way you train it is you train the meta learner on holdout data. Holdout data, right? You guys know what that means? Well, we're going to go through it a few times. So one approach to doing that would be leave out one cross-validation, and you would you would take one of your training samples and hold it out and move it over here. Then you would use all the rest of the training samples to train your base models. Then you would apply those base models to your holdout sample and produce a meta training sample just on that one holdout sample. Okay, so now you have one training sample for your meta model that was not influenced by having any of the base models trained on it. You don't want to train and evaluate on the same data. Remember that. Let me remove some of these crazy lines. Then you would move on to the next training sample, and you would hold it out, and you would take every other sample except for this second holdout training sample and train the base learners on every other sample except for your holdout sample. Then you would bring the holdout sample over here and apply all of the base models that you just learned to the holdout sample, and you would create meta training sample number 2. And that's what this leave out one cross-validation would mean. And that's how you could produce a training set for the meta model that's not influenced by any of the parameter sweeps or any of the other stuff that you did here. So you will generalize correctly. Then you produce that, you repeat it for all training samples, you train your meta model. Let me just show it to you one more time in pseudocode. You know, it might be a little bit overkill, but I found that some people like to kind of like see a figure of it, hear it conceptually, see it in pseudocode, and then it starts to click. So just do this one more little time. You would have your array of the learners that you're going to use: decision tree, logistic regression, neural networks, k-nearest neighbors. Now, k-nearest neighbors is something we haven't talked about yet. I think we're going to talk to it before the course is over. We may run out of time, but that's okay. Now, the first block here, you're trying to create the training data to train the meta model. And the way you would do that is you would iterate over all your train X. So samples is train X. And, you know, for S in train X, you would do all the loops that we've been talking about to train all of your base models. And I've kind of super simplified that here with this fit. But you and I both know that there's a lot more than just calling fit to train one of these models. But the point that I'm trying to make is you would take your train X and you would subtract this sample from it, and your train Y and subtract the sample from it. And then, right, that's where the extra loop is hidden. So you would build all of your base models with this kind of like hyper optimistic one line call, which would be much harder. And then you would append to your meta training set what you get by predicting for each of those models you just learned on the sample you held out. That's what that line says. So this would have an array with one number per base model here. Now, it's probably a good time to say that these base models could be doing classification if that's what you have available. They could be doing probability estimates. They could be doing a regression. And some of them could be doing one thing and others of them could be doing another thing, as long as your meta model is able to deal with those types of features. In general, you might think you're better off using probability estimates than classifications, because then the meta model, like if the decision tree says, you know, 0.75 and the logistic regression says 0.5, that contains more information than if the decision tree says 1 and the logistic regression says 0, because 0.5 happens to be below its threshold. You have a sense of, well, how close 0.75 is not like super close to that 1.0. So maybe that means a decision tree isn't super sure. We had a discussion about how those probabilities aren't really probabilities. 0.75 isn't really a probability even when you're trying to learn probabilities unless you calibrate it. The meta model can do the calibration for you. You don't need to worry about that. Okay, anyway, then for your meta model, you can use whatever you want. In this case, decision tree, whatever you want to do. We'll get in one slide a little bit of thought about how different meta models will affect what you're going to get out of it. But in essence, you call meta model fit on the sample that you produced in this first set by iterating over every sample. And then you'd, of course, do parameter sweeps, hyperparameter sweeps on your meta model. Now we're on to test time. And here is some sloppy pseudocode that doesn't quite do the right thing. But in order to ship your stack, what do you have to ship? You have to ship a version of each base model and a meta model that was essentially learned with that version of the base model, or that is relevant to that version of the base model. So what you would do if you did something like this leave out one cross-validation is you would probably go back and retrain all the base models just on every sample. And there, you would leave the meta model that you learned by doing the leave out one cross-validation, and then you would produce the base models that you learned on every sample. But yeah, probably wouldn't care too much. You could take maybe the last base models that you learned, the one that's learned on every sample except the very last one, at the end of this for loop, and you could ship those because, if one sample is 0.001% of your data, like if your training X is 1,000, 10,000 samples, something along those lines, you don't have to get too persnickety about that type of stuff. Anyway, you would ship those things, and then in the runtime environment, how you would do the testing is, again, take those shipped base models, run them on your test sample, produce X, and then call metamodel predict on that X. Right, now leave out one cross-validation sounds like a really slow, miserable way to do stacking, and you probably would want to do something else. If you have plenty of training data, you could take train X and take 80% of it for learning the base models and 20% of it for learning the meta model, or maybe 50-50. I mean, maybe that's another hyperparameter you could even play with, which is how much do I want to invest in learning the base models? Maybe if you're learning very complex base models, you need more data, but if you're learning kind of simple sets of simple base models, you might use less data, something you can play with. In general, in practice, you probably will have plenty of data so that you'll have more than you need to learn the base models and to learn the meta model. Maybe not, but And if not, leave out one cross-validation. A little bit more on stacking. The base models learn the concept different ways to inject variants. That's one of the things we're trying to do with ensembles. You can control the amount of variance by choosing which and how many base models, by choosing what hyperparameters those base models should have. Are you going to push them to a point where they're overfitting the concept, or are you going to keep them at a point where they have a high bias for the concept? It depends. You can do some parameter sweeps, but you should, before you set up the big parameter sweeps, you should have some sense of where you're going so that you don't set up a whole bunch of base models that do exactly the same thing and do a whole bunch of hyperparameter sweeps that are in that part of the region where your base models aren't helping each other, because you don't have time to do everything. So set it up so that you're in a good spot and you're probably achieving what you're trying to achieve when you decided to come to an ensemble. And then one way to think of it is the meta model learns how to value the votes of the base models, the various experts. And so how do you think about what meta model you want to use? Well, a simple one like logistic regression is going to put one weight on each of the features. And so in essence, it's going to weight the votes of the input models. It might learn that, hey, the weight 1 is 2. So 2 times the probability that X1 thinks the class should be 1. This weight here, weight 2, might be -4. It might be like super predict the opposite of what this model says because this model is terrible, right? Like those are the types of things it could learn, which is more sophisticated than what we were doing in bagging, maybe similar to what was going on in boosting, where each one got a vote proportional to sort of how correct it was on the weighted version of the training set it was trying to learn. And this one, you just learn how predictive each base model is on holdout data. In some sense, it's even more sophisticated than with boosting because, it's really directed on that holdout data prediction task. So that's what would happen if you used a linear model there. If you use a more complex model like a random forest or decision trees, you'll learn really complicated relationships between groups of these base models and which ones tend to agree and which ones tend to reinforce each other and which ones you might learn that if meta model 1 is correct, meta model 1 is the winner. Like if it says yes, it's always right. It has a very low false positive rate. So if it says yes, you just say yes. Easy does it. Otherwise, there's a lot of other things to do, and you have to combine the knowledge of multiple people to make up your decision. And like everything that we talk about in this course, we really just scratched the surface on what you could do. Another thing that is common, a trick you can use, is to take some of the base features and add them to the meta training set. Now, this could be pretty powerful because the base features might contain something like the context of what's going on. Here I got a little example where you could say, if the base features for an image represent that that's a dark image where it's like underexposed, then maybe Meta 3 is the model that does the best on underexposed images, and you want to use that predominantly to make the prediction. Similarly, on overexposed images, maybe X2 is the meta model that happens to learn that the best. And you could think of all sorts of information from the training set that could help you decide, oh, in this context, a particular base model is better, or another, one or the other. It might be common for you to use a subset of the features. Maybe there's certain features that talk about the broader context, like the exposure setting, for example, or, that it's a holiday, or that there was a sale going on, or something along those lines, or that the web server you're talking about is in the United States or not in the United States. And then maybe there's a whole bunch of like kind of content features or something along those lines, really the detailed features that these models really need to focus on. And you say, well, I'm just going to rely on the base models to deal with those detailed types of decisions, and I'm going to let the meta learner be simpler and just combine some votes with a little bit of extra context to know when it should count one vote more than the other. And of course, nothing is perfect. Stacking certainly does have some challenges. Number one, which is a little bit obvious, well, number one is tightly coupled, but number zero is that there's a lot of learning to do. And if you have to tune the hyperparameters for all these things and do all this hold out, leave out one, blah, 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 training can take a long darn time. That may or may not matter. Another is that this results in a really tightly coupled system where it takes a long time to train things. And, if you make a change, for example, to your decision trees, hyperparameters, that might make this feature more predictive, and that might cannibalize value that some of these other things were picking up. And then, the overall system might want to compensate by tuning the hyperparameters down here to pick up for different types of things, or to use that neural network's parameters and power to solve a different part of the problem. So anyway, a change to any part of this could change all of it, and you might have to do sort of extensive retraining to recover whatever value that you lost during a change. Another is that it is hard to know where to optimize, because you have a meta sample and it's wrong. What do you do? Who do you call? Do you say, well, that one's wrong because my decision tree didn't get it right? Well, maybe, or maybe it's wrong because the linear model was totally confused by something. So if you're going through this loop of feature engineering, hyperparameter tuning, look at your mistakes, cycle, stacking can make that a much more complicated task, particularly because each type of model here, in general, they could benefit from different feature approaches, different ways of creating the base features that go into them. So you might also be in a situation where a whole bunch of your features are really good for linear models, but are sort of confusing your decision trees, or vice versa, something along those lines. And the third thing here is that it's hard to track mistakes, which is a little bit like it's hard to know where to optimize. But if there's a bad false positive and you need to somehow override it, or you need to say, could that have been a bug? It's a lot harder to figure out where that is if you're dealing with all these kind of complicated models combined in a complicated way. Okay, now we've seen 3 ensemble algorithms, and these algorithms are sort of like the base algorithms we've been learning. In some sense, decision trees is an algorithm that takes features and labels and produces a model to get them. And ensembles are just slightly more complicated versions of those that tend to do well at bias variance trade-offs. Now we're moving into another topic. Now we're moving into intelligence architectures. And to some degree, an intelligence architecture has similar properties to an ensemble, which is I need to bring together a bunch of base models and potentially the work of a bunch of different machine learning scientists or machine learning engineers. And I need to put them into a working system in a way that they're accurate today, but that they'll be accurate 3, 6, 9, 12 months into the future. And so that's what we're going to talk about for the rest of this lecture, is how do you think about moving from an ensemble or a single model to a intelligent system that can be built by a group of people and maintained by a group of people who are different than the people who built it in the first place. And so what do you want? How would we like to think about setting up this conglomeration of models to achieve these goals? Well, first of all, you want things to be accurate, right? I mean, why are we doing this? You got to be accurate. The second thing you want is that it's easy to grow your intelligence. Now, what I mean by this is, let's say a new person joins the team. How many days is it from the day they sit down at their desk to the day they're able to deploy a positive improvement to the set of models, to the ensemble, to whatever it is that makes up the machine learning of your system? How much do they need to understand? How much of the problem do they need to know? How much of the interplay between feature engineering that's done 4 years ago and hyperparameter tuning that's done 2 years ago do they need to understand, so that when they try to make a change, they don't bump into or undo some like house of cards that was created by the person before them? We want a system that a new person can get into. They can easily make a change. They don't have to understand everything to make progress on something. The third, I guess, is loosely coupled. And maybe this is starting to sound a little bit like traditional software engineering, but you don't want to have models that depend too heavily on one another. For example, in a stacked setup, a base model might overfit to something, and then the meta model might unoverfit to the thing by understanding the context. Now, if you change the base model so that it no longer overfits, the meta model, which is trying to also undo that problem, will now potentially be creating new problems. You could say those models are tightly coupled. And when models are tightly coupled like that, it gets hard to deploy things, because in order to deploy one thing, you might get into a state where you have to deploy everything. And it's worse than that, because in order to deploy one thing, you might be in a state where you need to completely retrain every model in your system from scratch, because you've allowed these interdependencies to creep through the system. And I've been on multiple teams where it got to the point where we're like, yeah, we're just not shipping anything else, just leave it alone, right? It's whatever you think you can do by adding that feature. It's not worth the heartache of trying to track everything down to reship and re-verify, or retrain and re-verify all those models that make up the input to where you're trying to make your change. So loosely coupled, something you definitely want. Comprehensible in terms of mistakes. And what this means is, like, when there's a big false positive and your PM calls you and says, my goodness, we have to fix this, who do you call? Do you know which model in your system contributed to that mistake? Do you know, is there a particular model that's responsible? Or do you have to do an end-to-end sweep and be like, well, this model thought a little bit of this and that model thought... Anyway, so the easier it is to track down mistakes, the better well-organized the intelligence of your system is, the set of models in your system are. Now, another thing is, it's good to be able to measure the value of each part of your system. I've been on teams where there were multiple layers of machine learning, each of which is slightly transforming the input data. And, you take a look at them and you're like, does that third layer really do anything today? We're spending a good amount of money at runtime running those models, but are they still actually adding any value? Or is the new layer we pasted on top of all those other layers because things were too tightly coupled that we couldn't fix it where we wanted to fix it? Maybe we've cannibalized all that value. So it's very nice if you can measure the positive impact or negative impact of each part of your system. The final thing is supportive of team. And the point of this is just, you can set up a machine learning architecture where there's one model that rules them all. And the situation you could be in is it's an important problem. You want to have multiple modelers working on it, but you can only really ship one model. So if one of them succeeds, the others by definition fail. And anytime you want to ship a change to the model, you have to beat the finely tuned system that the previous engineers or the previous machine learning scientists have done. And they kind of don't want you to beat their system and turn it off. And you can end up with these weird political, irritating situations. What you'd rather have is an intelligence architecture where when a person makes something better, it doesn't cannibalize from the rest of the system. In fact, what it does is it solves problems for a another one of the people working on your system. So that person is like, whew, thanks for taking care of that for me. They're not like, you just killed my review by making me deprecate the system that I loved and worked on for so many years. So there are 6 properties that you want to think about when deciding what type of model, what type of ensemble, what type of interconnection between models to use when I'm developing the machine learning in my system. We're going to pretty quickly, I think the very next lecture, possibly, start talking about some design patterns for machine learning, which will look at how these issues were handled in real systems, what went well, what went poorly. But for the rest of this lecture, I'm going to go through a few common patterns, a little bit more abstractly, and how they relate to each of these 6 properties. And let's start off with this example, which is a very, very simplified diagram. On this axis is the complexity of the feature engineering that you do across your whole system. And on this axis is the kind of meta or interdependency between model complexity that you have within your system. Now, what we just talked about was stacking and using stacking as an algorithm. And if you look at it on these 2 dimensions, you basically have one feature set for your training problem. You have like X train. Stacking doesn't really talk about creating other feature sets. What it talks about is taking that feature set and then learning a bunch of different base models and learning a meta model on top of it. So the fact that you're learning multiple base models and then combining them with unrestrained machine learning makes that meta complexity relatively high compared to the things that we're going to draw below it later. Another way you could think about organizing your team is that you could split up the work on the base models, and you could tell each of the machine learning people on your team, hey, you go build it with a logistic regression, and you do whatever feature engineering you need, and you build your own feature set for your logistic regression. And then when you're done with that, we're going to have other people working out from other approaches, and we'll build a meta model on top of all of you. And you can see here, I call this the Kaggle pattern, and I think maybe I'm the only person who calls it that. Now, Kaggle is a website that has machine learning competitions. And the idea would be, maybe you've heard of the Netflix challenge, where Netflix publishes some of their data, and then teams come in and try to get the most accurate answer to the Netflix problem, and then the website Kaggle keeps track of all the submissions and makes sure nobody's cheating and shows you leaderboards about how far, who's winning, how far are they winning against the other people, how are they doing against the Netflix benchmark solution, has anybody beat it yet, all that workflow around it. And so you might go on for months and months with teams of people working on a single problem, changing places on the leaderboard. It can be a lot of fun. In previous iterations of this course, we did Kaggle competitions. I thought they were a lot of fun. Many students thought they were a lot of fun. Some students thought they were pretty stressful, so we're not doing them this year. But the point is that a good way to organize that type of effort is to take all your machine learning people and let them run. Let them each attack the problem using their best skills, the techniques they know, the models they know. So if you have a team of 5 people, you have 5 people highly tuned models for that, whatever the problem is that you're trying to solve on Kaggle. And then in order to combine those, you don't have them talk and say, ooh, this technique, that technique, blah, blah, blah. Let's re-engineer a single model that has the best of everything we're doing. No. You just train a meta model on top of the work of those 5 people, and you ship whatever that says. And so it has a lot more feature complexity than stacking, because you have different feature sets for different models being combined by this meta model downstream, blah, blah, blah. And it has a similar meta complexity because the models are at the end combined through this kind of tightly coupled, very specific, rigid form of training a model to make predictions with the outputs of those models as features. So that's a kind of tight coupling way to do it. It's a great way to get accuracy. It's the Kaggle pattern because I have heard of multiple teams that have won Kaggle that use this pattern. I'm sure there's other ways to win it. But that is the type of thing you want to do if you're chasing accuracy for a single point in time, a single problem, a single victory. You probably want to do that. But most systems that most of us are going to be working on aren't that. They're chasing accuracy every day, every week, every month for the next 5 years. And in that sense, both of these 2 patterns, because of the meta complexity, can lead you into troubles and are probably, like, I would say certainly, probably, but very probably not the right thing to do. And so what can you do? Well, you can limit the complexity you allow into the meta layer by, learning base models on maybe subsets of the features and then combining them with a very simple handcrafted rules or a highly constrained model, like a decision tree with 3 nodes or something along those lines. So you can actually see how the combination's being done and modify it if needed. And you could think of this as business logic in that, like, let's say you have a model that detects, is the image properly exposed? And you could have some business logic that says, if we think the image is not properly exposed, never use it. Never auto post it to my Instagram or wherever it's going to post the sites, because we just don't ever want to allow that thing through. Even if some of the other models say, hey, there's a face in there and that person's smiling, I don't care. It's underexposed. Our site doesn't want underexposed stuff on it. So you might have some simple meta model that plucks some of the base models and says, like, these are just conditions that we don't allow, leave them out, no matter how an expert machine learning system would want to make a different decision. Our business just doesn't do that. And that's all great and all, but you often will have things a little bit more chaotic in terms of the feature and the modeling complexity for the base models, where you may have a team of people running in different directions, creating models, but then you still want to bring them together in a way that allows you to control and run your business. So you want the best of both worlds. You want this Kaggle patterns power where you can unlock the potential of a set of smart people, and you want this business logic control over what you're doing so you can set up guardrails and have your system not go crazy. All right, well, let's look at some of these in a little bit more detail, hopefully not a ton more detail. But if you're looking at that upper right quadrant, saying intelligence architectures for a team accelerator, kind of the Kaggle pattern, something along those lines, you might start off with a model like this, and we'll get into a spam in detail in the next lecture, but you might have a filter that looks at the content of the message and tries to decide if the message is spam or not. That's something you could do. That's probably where you would start if you're going into this space. But then you're going to want to do better. So you might go off and create another type of feature, and you come up with reputation features. Now you have to train a new model, which is p-spam with content and reputation. Maybe that's the same model. You've just created it once. And so you go and you just add the features through feature engineering, train it, move on. Okay, but now you think of a whole bunch more things to do. Now you have 1, 2, 3, 4, 5, 6, like a newsletter detector, looking at what the message links to, evaluating the images. So you have 6 or 7 different, highly conceptually different approaches to telling if something's spam or not. And you engineer them all into a single large model. Xtrain contains features for all of these different types of information. You can totally do it, but that is a very, very tightly coupled way to put this information together. It's super painful when you have multiple machine learning engineers changing the feature extractor, this monolithic feature extractor simultaneously, not necessarily great. One thing you could do is to decouple it. You could have one person working on telling if a message is spam based on the content, one based on the reputation of who sent it, images, blah, 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 and then train a meta model. So already this step from a single monolithic model to this, pseudo-stacked model, but where each base learner has a separate set of features, that's a strong positive forward step. And if you wanted to take this and, you could argue, is this setup with the meta learner more or less accurate than the monolithic model? Is it more or less easy for a new person to come in and add to the system? Is it more or less coupled? Are the mistakes more or less comprehensible? Can you tell better with the monolithic model or with this pseudo-stacked model how much each feature set is adding to your overall accuracy? And which one would be easier just in general to keep your machine learning scientists from strangling each other and not getting stuck in a lot of politics? And, that's sort of an inside joke, but it never happened to me. I've never been involved in politics. I don't do that. In some sense, this is my interpretation of it, is that this can be quite accurate, maybe even more accurate than trying to do things as a monolithic system. But it has negatives on most things. And it's just sort of okay of being supportive of the team because there may be, I don't know, cannibalization between these, or what is a link versus an image. Maybe people would disagree on that or whatever. That's my assessment of this one. Your assessment might be different, and on different teams, you will bump into different of these challenges, depending on how many people you have working, how cohesive your team is. But this is not a management class. This is a machine learning class, so we'll leave it at that. Now let's look at another way of doing this, something on the lower half of that chart we started with, where we have a less complex meta model, or where we want to take the meta model and let it express business logic or business constraints that will help us in the broader application, but might not be the most accurate combination of the information according to like optimizing loss, blah, 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 blah. Here's an example where instead of combining everything into a single model, we instead take the reputation filter first. And we say, if the reputation of the person who sent it is known to be good, deliver the message, no matter what. Now, you might say, well, look, there's a lot of information in the content. What if somebody who has a good reputation sends some really crazy content? Wouldn't you like to delete it? Maybe that would be more accurate, but that's not what we do with our business. Once you've established a good reputation with us, you can get to the inbox. You might ruin your reputation, but that's a different discussion. What are some other forms of business logic you could apply? You could say, if the message is a newsletter, don't delete it. Maybe move it to the junk folder, but just don't delete it because users like newsletters and they're not that offensive anyway. If the message links to a malware site, like if we look at the links and the link model is very short links to malware site, just delete it. Don't call the content filter. Don't let them try to trick you. It links to a known malware site. Delete. Done. And then you might even get beyond that and say, hey, not just spam versus not spam, but maybe we have other properties we know of the message, like it seems important, it seems urgent, different things like that. You can use all of those in making the prediction of if it's spam or not, but you may also want to break them out and use them to power other parts of your system or your experience. So sometimes it's nice to have an architecture that allows you to do that. And further, it's nice to decouple your problem into subcomponents that are reusable across different parts of what you're trying to accomplish with your product. Now, I think I did a little breakdown here, again, according to these criteria. The accuracy is probably okay, probably not good, right? The previous one where you're actually training a meta model is gonna have better accuracy than some handcrafted logic you do. And then really, the point of all these question marks is you can make some terrible logic. You can make this problem extremely difficult if you try to do too much in this logic layer. But if you have a simple, well-crafted logic layer, like we're going to see in the next two examples, this type of approach can get you a long way. So let's move on and do one of those. One simple way to lay out the logic I call model sequencing. And in model sequencing, you have a default answer. That is, you're kind of just passing through with a 0. But what you have is a series of models that can potentially override that default answer. So if you were looking at a phishing web page, you might say, look, most web pages are not phishing. So our default's going to be like, no, that's not a phishing site. But now you have a model that looks at the content very deeply. Now you have a model that looks at the images and looks for brand violations, looks for logos that shouldn't be on that site. Now you have one that looks at the servers where it's hosted. Have there been other phishing sites there in the past, et cetera, et cetera, et cetera. And if any of these models trigger, you trigger a change to that default answer, and then you output a phishing site. You can achieve an overall false positive target pretty easily by tuning the thresholds for each of these models to a fixed false positive target, or like you have a false positive budget that you spread across them. So in order to create a new model to add to the system, you have to get somebody to give you some false positive budget, get somebody to insert you at the right point in the list, and then tune your threshold so that you achieve that false positive target. As the person running this overall system, if anyone starts violating their false positive target, you can measure it very quickly, you can kick them out. And remember, we talked about orchestration, and those are the people who run a system day in and day out and tweak and tune all the models and control the architecture. Well, this is where an orchestrator would be involved. And they'd be responsible for making sure that these models play well together. And monitoring it and making sure nothing's getting out of whack and ripping things out that are causing problems and reaching back to the people who created these models and say, hey, you have to do some sort of an update. That sort of, in some sense, that's the machine learning operations of watching the system and make sure it's doing what you're doing. For example, each false positive can be traced back to the model that caused it. And, in this sense, the way that this channel would work is that you would call models in sequence until one of them says 1. And then you could conceptually stop calling every model downstream of that because the answer's already 1. I don't care what they say. Somebody flagged on it. We are calling it phishing. But then you can also log that model number 2 was the one that said 1 in that case. And then downstream, if you have some sort of a closed loop that's getting feedback from users, you can attribute any like error reports. And you could say, hey, model 2 is causing most of our errors. Let's go figure out what's going on or why its false positive rate is too high, something along those lines. And it's nice in that anything that gets through the stack of all the models, well, that's fair game. Any model could improve itself and start catching the mistakes that are beating the whole system. And maybe that's slightly competitive, but maybe it's not so bad. It doesn't matter if 2 models can catch the same fish. In some sense, the models higher in the stack might get the credit for it because they are the ones that get called and they're the ones that are logged. But in some sense, it doesn't really matter. If you're making progress, you're making progress. So if we go to this chart here, the accuracy is, again, I just say okay because you might say minus. I said okay because compared to a meta model where you're combining information across all these base models, you're certainly worse. That meta model approach got a couple pluses on accuracy, whatever, fine. But this type of a setup is nice in every other dimension. And sometimes being easy to grow because anyone can just come along and jam in a new model, even a very simple model that's catching something that's, like then an emergent problem. It's loosely coupled because you can change one model without affecting any of the other models. Maybe the overall system's accuracy goes down a little bit if you remove or mess up an important model. But you're not going to need to go and retrain the other models when you remove a model. It's just an opportunity for the other models to start catching new problems. It's comprehensible because you know who made each statement. You know who made each mistake. And the measurability is okay. Like I said, as an example is passing down this chain, the first guy to have an answer gets the crack at it, but you could conceptually take some percentage of your data and run it through all the models and log how much value each of those would be adding to the system independently. And then supportive of the team, I think it's much more supportive of the team than the other ones because people can silo to some degree, and you don't always want your team siloing, but sometimes it's good to allow people to focus and not have to have a lot of communication overhead to make progress. And yet it's easy to plug in and you're not really hurting somebody else's work by doing your work. All right, now the final method I'm going to talk about is partitioning by contexts. And this is a common thing to do. For example, if you're classifying websites, you might know ahead of time, the orchestrator working on your system might know that dealing with large websites that have a lot of traffic to them is a very different problem than dealing with small websites. Because, for example, on a large website, you can see how users interact with it because you have those interactions in your logs. Versus a small website that you've never seen before, you have to rely a lot more on, let's say, static properties of who does it link to, where is it hosted, et cetera, et cetera. Okay, so that's something, that's some domain knowledge. And you could just use your domain knowledge to say, hey, there's some really fantastic behavior-based features that modeler number 2 can use, but those features aren't going to be present here. And in order to learn a model that can do well in the presence of those features and the absence of those features can be quite difficult because those features can really overwhelm other important features. So we're better off making that split to begin with. That's a nice start. The orchestrator can carve the problem up, and then each leaf is solved by a model heuristic or another architecture. For example, you could have a whole model sequence like we described on our previous slide that you use on small websites, and a whole nother intelligence architecture that you use on large websites. Like, for example, you might say websites in the EU versus websites in the rest of the world. There's different regulations, something along those lines. So just intrinsically, we know that there's different features that are going to be applicable. So let's just simplify that problem, split it, and go. One thing that's nice about this is that often when you're using machine learning, 50 or 60% of the overall problem can be solved really easily. You could write down 3 if statements that solve a really large chunk of your problem. Write it down, solve the problem. Use an architecture like this where model 1 is very, very simple if statements applied in carefully chosen contexts where those if statements are supremely accurate or just like must be true. And then you don't have to let your machine learning algorithm waste parameters learning that stuff and deal with noise in the data and deal with problems and like spend a lot of its attention and a lot of its power over there. You have the machine learning focus on the part of the problem that the machine learning is actually needed for. Often this results in better, more maintainable systems over the long haul, where you're not chasing weird problems because that boundary between what's easy and what's hard becomes unclear to the machine learning algorithm, even though it remains clear to a human. So partitioning contexts, very, very good technique. I like it a lot. And I like it a lot because I put a lot of pluses over here. and again, accuracy, you're probably better off doing a meta model for accuracy on day 1, but on day 300 and on day 600, you might not be better off. You might be benefiting from these other pluses that are listed there. Okay, anyway, so there's an introduction to what intelligence architectures are and why you might use them, and a few approaches to it. Quick summary of what we covered today. Stacking is an ensemble method that learns a set of base models of different types, whatever you want, and then uses a meta learner that takes the base model's predictions as input and tries to predict the original labels. You got to train that meta model on holdout data. Otherwise, it's going to be too optimistic. It's going to overfit. It's not going to be good. And you want to select the base models based on the bias variance properties. So you want to make sure that the base models learn the problem in different ways and that the meta model has enough complexity to understand the interrelations of the base models and to figure out how to combine their votes in the various contexts that it might see. Organizing your models is more than just using ensembles. And even though stacking seems like a perfectly good way to run a large modeling operation in practice, it's not. It has some serious disadvantages for working with a team and working well over the long haul. So organizing your intelligence and the way your models interact is critical to long-term success with machine learning. Stacking, like we just talked about, but some other approaches include simple heuristics or business logic to combine models, provide guardrails for those models. Model sequencing is a good technique. And then the final one we talked about was model partitioning, where you split up the instance space by variables that you know are meaningful and that you know will require very different modeling approaches ahead of time. All of these approaches restrict flexibility in the short term. And it's very easy to say, like, this is terrible. I'm a smart math person. I want to optimize. Why are you tying my hands with these things? But they're going to lead to long-term benefit. And it's quite often the case that you can ship the most accurate thing on day 1, but that's not your goal. Your goal is to have the most accurate thing every day for as long as your system's running. And without careful planning, you're going to end up with spaghetti intelligence that you can't change, that you can't improve, that you can't hire new people to work on. You're going to get yourself stuck. All right, well, that's the end of our talk about ensembles, bagging, boosting, stacking, intelligence architectures. I'll see you next time.